Okay, so we're going to do another example where we're just going to look for the eigenvalues and the eigenvectors of this matrix right here. So 1, 4, 2, 3. So the first thing we're going to do is take the determinant of A minus lambda I. Okay, so we're going to put the lambdas in the diagonals in the subtraction. That's 1 minus lambda. That still goes 2. That's 4. And that's 3 minus lambda. Okay, so that's going to equal, so that's 1 minus lambda times 3 minus lambda, and then minus 2 times 4, which is minus 8. Okay, so this first part is just going to be, well, that's a 3. And then we have a negative 3 lambda and a negative 1 lambda. So negative 3 lambda and negative 1 lambda would be a negative 4 lambda. Okay, and then plus lambda squared minus 8. All right. Now let's reorder this so that it looks pretty. So that's going to equal lambda squared minus 4 lambda minus 5. Right? So that's going to become lambda plus 1 times lambda minus 5. And we're going to set that equal to 0. Okay, so what are we going to get from this? We're going to get that lambda 1 is going to equal negative 1, and that lambda 2 is going to equal 5. Okay, so those are the eigenvalues for our matrix. Okay, so that's step 1, eigenvalues. Now, step 2, we're going to look for our eigenvectors. Okay, so let's go to step 2. All right, so what we're going to do is we're going to find V1, and so we're looking at A minus lambda 1I. Okay, that's going to be, okay, so our matrix, that's 1, and then minus lambda 1, that's minus, now negative 1, it's 4, that's 2, and this is 3 minus negative 1. Okay, so that's A minus lambda 1. Okay, so what are we going to get from this? 1 minus negative 1 is 2, that's 4, that's 2, that's 4. Okay? So just as in the previous problem, when you take the determinant of A minus lambda I, okay, what happens is you're setting it equal to 0. By setting the determinant of A minus lambda I equal to 0, you are basically creating a linearly dependent column space. Okay? And so, since it's linearly dependent, we're going to get a free variable. And so if I take that top row and I multiply it by negative 1 and add it to the bottom row, everybody gets knocked off. That's 2, that's 4, that's 0, and that's 0. Okay? Well, like in my the previous problems we've done in this class, I want my pivots to be 1. Okay? So I'm just going to go ahead and say, I'm going to divide this guy by 2. Okay, so well, 1, 2, 0, and 0. Okay, now this has to act upon the 1 has to produce the 0 and 0. Okay, so this one says x1 plus 2x2 equals 0. Or that x1 equals negative 2x2. Okay? So, v1 would equal negative 2 and 1. And then, like we discussed earlier, the off camera, that's not unique. It can be multiplied by a constant. Okay? But you want to keep it as just one vector because then when you solve the differential equations, you don't want the two variables floating around. Okay, so let's check our work real quick. Okay, so if matrix A acts upon this, it should equal lambda 1 v1. And our lambda 1 is negative 1. So let's have our matrix act upon that. Okay, so we have 1, 4, 2, and 3. Now act upon negative 2, 1. Okay. Well, 1 and 4 acting upon it, that would be a negative 2 and a positive 4. So it could be a positive 2. Okay. Now, 2, 3 acting upon it, the first one's going to be negative 4, and the other one's going to be 3. So negative 4 and 3 comes up to be a negative 1. Okay, and that does equal negative 1 times negative 2 and positive 1. So, positive 1. So we do have the correct first eigenvector, that negative 2, 1. All right? So let's find B2. Okay. So we're looking at A minus lambda 2 pi. Okay, my lambda 2 is 5. So that's going to be 1 minus 5, okay, 4, 2, and 3 minus 5. Right. So what are we getting from this? We're getting negative 4, 4, 2, negative 2. And once again, if I took the top row and then multiplied it by 2, add it to the bottom row, that would be this much. So, now negative 4, 4, 0, and 2. You know what? Let's go ahead and divide by that negative 4. Okay. 1, negative 1, 0, 0. Now this guy acting upon B2. Equal 0, 2. Okay, so what does that tell me? This is a free variable right here. So remember, whatever you're doing, you're going to flip it to the other side of the problem. So this is hitting x1 minus x2 is going to equal 0. Okay? Or the x1 equals x2. Right? So b2 would just be 1, 1. Off the screen. All right? And now let's check our work. 1, 4, 2, 3. Acting upon 1, 1. That would equal 1 plus 4 would be 5, and 2 plus 3 would also be 5. And so that equals 5. Times 1, 1. one, yes, we did get the correct second eigenvector for the matrix.